The remainder of Chapter 7 that we're dealing with now is mostly about how we can separate things out from solutions. We've probably done enough equilibrium chemistry to realize that it would be really nice if we could get just one analyte separated from complicated matrices. One way that we do that, particularly for metals, is by digesting a sample. Digesting a sample can help to dissolve the metals, but it can also simplify reaction matrices. The most common digestion acid we use is nitric acid. Most metals are reasonably soluble as nitrates, right? One of the most soluble forms of a metal is with a nitrate salt. We also know that nitric acid is a strong oxidant, so that it can oxidize organic matter, removing those components from the matrix. It's actually really interesting. We'll do fuming nitric acid digests, and when we do that, it lets off nitrous oxide. We have a microwave set up for this too. Digesting in the microwave can bring down reaction times and volumes, making it much easier to prepare the samples really quickly. Some analytes shouldn't be digested. Pretty much anything organic would reduce to nothing, or more accurately, oxidize to nothing. We have a wide range of separation techniques that can isolate some analytes from others, but in most cases are less destructive. Centrifugation, really fast spinning, is a convenient way to separate out heterogeneous, having different phases, components of a solution that are of varying mass or densities. So this can separate out solids from liquids, but it can also help to separate suspended particles like cell components. We sometimes even use it to accelerate the separation of two liquid phases. Another way of simplifying a matrix is to cut out signal from certain analytes by masking the analytes. Masked analytes remain in solution, but their availability and therefore their interferences can be greatly diminished. So we react them to make them less active in solution. One of the oldest separations comes from the world's first chemists. Even before there were alchemists, there were brewers and distillers. Distillation is an effective way of separating two liquids with different boiling points. The archetypal example is ethanol and water. It's not quite as simple as water has a higher boiling point than ethanol, so ethanol boils off first. Whenever we have a mixture, their boiling points will be altered by colligative properties. So a mixture will start boiling lower than expected and finish boiling higher in a lot of cases. A mixture that is mostly a high boiling impurity, like the A in the picture, will evaporate as an impure mixture. Because the analyte is lower boiling than the impurity, there will be more analyte in the vapor phase. So we'd see that the mixture would move over to be in the vapor phase. If it recondenses, more analyte will fall out into the liquid phase. So now it has a larger concentration of the analyte. We could repeat going from C to D and then condensing out and repeat as many times as we need to purify the mixture by multiple distillations. Some analytes can be isolated from others by phase change. The most obvious is the controlled laboratory version of the baking soda volcano. Our carbonates can be converted to gas with an acid. Many of our polyatomic ions are related to gaseous or volatile species and can be converted by acid or base. Another form of materials isolation should look familiar, at least to one of you. It's called the Soxhlet apparatus. A Soxhlet apparatus cycles hot solvent through a solid phase held in a sock, and periodically cycles it back where it gets recycled. Because the recycled material is generally relatively pure and doesn't have much analyte in it, it allows a large amount of the analyte to be collected in the solvent on the bottom while the solvent ends up being recycled. The most common analytical separation is an extraction, which moves analytes and interference into different phases. The phase transitions are always in equilibrium, so even efficient extractions are often repeated. We can often encourage moving between those phases by using concentrated salt in the water phase, or by making it acidic or basic, like Kimberly's independent organic project last year. To see clearly how this would work, let's look at A- in the aqueous phase of the drawing shown. A- is ionic, but if we add acid, that A- becomes HA. It becomes neutral. Now it's less polar and can move to the organic phase. We can do a similar thing to bind metals out of the liquid phase. It works best when a ligand that can bind a metal has more affinity for the metal than the hydrogen, because if the ligand binds to hydrogen, it often can also move into the organic phase on its own. Separations don't just matter in the lab. We'll constantly be seeing phase exchanges in our natural systems. Things will be constantly moving between phases, for example, in the soil and groundwater. Groundwater is always going to be in close contact with the soil, which is typically much less polar. So the acidity and presence of other compounds can change how things move between the soil and the groundwater. And since the groundwater moves a lot more than the soil, it can also change how mobile a pollutant is. Many molecules that can move between soil and water are characterized by an equilibrium constant, called the KOW, which stands for the octanol and water partitioning coefficient. It's an equilibrium constant. The KOW uses octanol instead of soil to estimate soil characteristics. That's a lot easier to measure and a lot easier to remain standard because soil can be all over the place. But pretty much the idea is that the water is polar and the octanol is mostly nonpolar. So here we have three compounds. Benzene in the top right, which is nonpolar, glyphosate, the major component of Roundup, in the top left, which is polar, and copper sulfate, which is used in a lot of organic, in a farming sense, pesticides, which is ionic. The glyphosate moves quickly into the aqueous phase because of all the polar pieces, the OHs on the phosphate, the carboxylic acid, and the amine. The benzene would not move into the organic phase. It would stay, or the benzene would stay in the organic phase in the octanol, or it would stay on soil. It would not move into the aqueous phase. Copper sulfate is actually generally insoluble enough that it wouldn't go into either phase readily. Now here's the really exciting part. The compound in the bottom right is called MTBE. It stands for methyl tert-butyl ether. It was used for a really long time as a fuel additive. Incidentally, benzene, again in the top right, is also a component of fuel. Now, remember how when we make water more ionic by adding salt to it, it makes nonpolar things fall out? Well, it turns out the opposite can happen. MTBE is less polar than water, but it can still dissolve in water. When it dissolves in water, it will take other nonpolar things along with it. It's an emulsifier. It takes benzene, a carcinogen, into the water. And that's why MTBE, a relatively safe compound, actually becomes really dangerous. It's a type of compound called a phase change catalyst that encourages nonpolar benzene into the water.